Welcome back to the Lowdown on Physics. This is Screencast number 4 in the Unit 4 Physics VCE series on electric power. Today we're going to look at the relationship between force, current and magnetic field and how that applies to the principle of an electric motor. The basic operating principle for a motor is really quite simple. What it does is send an electric current through a magnetic field, and that wire is going to experience a force. Now, we're going to focus on DC motors. We don't need to look at AC motors. And basically what an AC motor consists of is a wire loop containing electric current inside a magnetic field. So the two key features that we have are the current carrying loop. So we've got our loop here carrying a current, and we've got a magnetic field. Okay, that loop needs to be in a magnetic field where part of that loop is perpendicular to the magnetic field, so that current can experience a force. So we've got a diagram here showing current travelling there, we've got magnetic field up there, and so therefore the force is out that direction. Okay, and then the same down the bottom, we experience a force in the opposite direction. What would happen if we experienced a force in the same direction? We'd never get any turning, yeah? So it's very important that the force on either side is the opposite direction so that we actually get the loop to turn. So we've got this little Java applet here from a website, and what it shows is when the current is flowing through this loop, it's experiencing a force. So this is using our FBI rules, or right hand palm rule, whichever you prefer to call it, to produce this turning effect. Now what happens if we change direction? Change the direction of the current, the FBI rule reverses, the force goes in the opposite direction. Now you'll notice the force sort of just disappears at this point here. We're going to come back to the importance of this in just a moment, but partway down we have an issue with the force. So we'll go have a look at that now. So we'll analyse in a bit more depth what's actually happening to the wire. So let's say we're looking at this side on now. So we're looking, say, straight on at that side edge. We've got current going in, coming out of the page here. We've got current going into the page there. Okay, so we're looking from this end, and so we've got the current going into the page there. We've got the current coming out of the page there. Now, using the FBI rule, we've got magnetic field coming across here. We've got current out, that produces a force up and a force in the opposite direction. This causes the coil to begin to rotate. As it rotates, the force goes up. At this point, it sort of reaches this point where the force is now up. What's that going to do to the rotational effect? This is actually going to, as it continues to move around, sort of the momentum or the inertia is going to take it around. However, the force is going to cause it to swing back, so it's effectively going to oscillate until it loses all its energy and come to a stop in this position. So after 180 degrees, so assuming that this started the opposite point down here and rotated, it will spin around until it gets to here, and then it begins to reverse back. So this, I guess, highlights some problems with the basic DC motor. Okay, we've got this part rotation, so it's only going to make a half turn, which isn't very useful for us. And the twisting effect decreases as the coil turns. We're going to have less force here because it's on an angle than if we did, or than it does down here. We don't have any twisting effect up here, and we only have a small force unless the current's actually quite large. And really, the whole magnetic field is quite weak because there's all these air gaps in here. So how do we overcome these problems? So efficiency, and this is where there are a couple of marks guaranteed in your exam. How do we make this motor better, or what's the best way to improve the efficiency of this DC motor? And then you can kind of flip that round when it gets to generators and AC generators, and how can we improve it? So first thing, to make sure it keeps spinning, and this is what I highlighted, this little funky little thing on that animation, is we need what's called a split ring commutator. And what this does is reverses the direction every half a turn. So every half turn, the direction of the current in the coil changes, and that keeps the force on the left-hand side always going one direction, and therefore the torque is always in the same direction, so it's going to keep rotating. Okay. Often there's a question asking what's the purpose of the split ring commutator. Reverse the current after a half rotation, ensure the force on the same side always acts in the same direction to ensure torque in the same direction. That's your answer. It can be a 2 or 3 mark question. So really, it's a bit of a gift if you've got something like that down and you understand that. How else can we improve it? Well, if we add more coils, then we have something in the field all the time. So if you have 2 coils at right angles to each other, one of them's, when one's got no force on it, the other one's got maximum force. We can use a number of turns. So a number of turns just means a number of loops within a given coil. So if you want to work out the force, if you've got 20 turns, you multiply the force on a single strand of wire, multiply that by 20, will give you the force for all 20 turns. We can use a stronger magnet, or we can use an electromagnet. You can increase the size of the coil. Okay, so increase the L. So think about this equation. We increase B, we increase L. Then we could increase perhaps the current. What else? We can wind the coils on an iron core. What this does is reduces the air gap, but it increases the strength of the magnetic field acting around those coils. And instead of flat magnets, we can use curved magnets. That means that it's perpendicular to the coil for a lot longer of the rotation. Okay, so here we've got split ring commutator. So you see there's a gap in it. So while it's touching this side, it's attached to the negative, and that means, the current's moving in one point. As it rotates, it goes through this point where it's no longer touching, and then the other side touches the negative terminal and causes the current to go the opposite direction, but ensures the force is always on the same direction. We've got multiple turns. Okay, this here is called the armature. It's what's rotating. The brushes are what attached to the split ring commutator. Just a little bit of terminology there. Okay, and then if we were to have a second coil this way, then we'd split the split ring commutator into 4 parts. So 2 attached to one coil, 2 attached to the other, to maximize its contact when it's at right angles to the magnets. Let's look at a very basic calculation motor type question. So firstly, we've got the coil here is a 4 centimeter square, so that means each of these sides here is 4 centimeters. It looks a bit more rectangular, but anyway, we'll deal with that. Consists of 20 turns of wire. It has a current of 5 amperes, and the field strength is 0.8 teslas. So firstly, what are the forces on each side? So we've got to calculate F. Now, what we haven't been told or shown is the direction of the current. So let's assume a clockwise current is going through. So the force equals NBIL, so number of turns times the magnetic field strength times the current times the length that's in the field. So here we've got 20 turns, 0.8, 5 amperes. Now, units. They'll trick you with this one or try and catch you. 0.04. So the force is 3.2 newtons on each side. What is the torque on the coil? So the torque is force times distance if we think back to unit 3. So we have how far from the point of rotation times the force. So we've got 3.2 times 0.02, and we're multiplying it by 2. Why are we multiplying it by 2? Because you've got force on this side causing torque, you've got a force on this side causing torque, so you account for both of the both armatures. And we get a torque of 0.128 Newton meters. Alright, so let's look at, that's the most basic form, and that's where you'll probably get questions around that, about making them more efficient. What about more advanced motors? So basically, often you'll get an electromagnetic coil that's going to be spinning around. You'll have it on a soft iron core. This maintains the strong magnetic field and allows maximum interaction, I suppose, to produce maximum force. And normally we have a series of different coils offset to each other. So here, I think, we've this animation I think is a little bit incorrect, because really we're swapping before we actually hit the magnet. So really it'd be swapping it about here and swapping again as it gets out the magnet. But it gives you the idea that there's that changeover point there. And the idea is that you're producing a more consistent torque, or a constant torque, so that it's not sort of jerky as such. It sort of continually has high amounts of force. So how do we improve torque? Again, this sort of relates back to how do we improve the simple DC motor, and it'll be one of these two questions that you're going to see in your exam. So firstly, you want to increase the length and width of the conductor in the field. Increasing the length increases the force. Increasing the width means you've got greater torque. You can increase the number of turns. Again, that increases the force. You can increase the current, which increases the force. You can increase the magnetic field strength, and that increases the force. You can do that by either using bigger, stronger magnets. You can use electromagnets, or you can add the armature, that soft iron core, to maximize that interaction between the coil and the magnetic field. So that's the basics to an electric motor. It's really not a lot to it. So good luck, and we'll do some questions in class and have a bit of a look at an electric motor.